We are now going to talk about the Great Oxygenation Event, which is very important because animals need oxygen. I want you to draw a picture with me, and I'd like you to use a fresh piece of paper for this and maybe use it sideways in the landscape mode and take your notes on another piece of paper. I'd like you to draw a straight line across your paper and maybe use a ruler, and then draw two lines at the end to indicate the ends of that line, and then draw another little hatch mark in the middle. Draw two more hatch marks in the middle of those, so you have something that looks like this. This is going to be a geologic timeline, and we're going to put the present on the right-hand side, and then we're going to go back 1, 2, 3, 4 billion years, or 4,000 million years. Not quite to the beginning of Earth history, which is 4,600 million years, but this will be good enough for our purposes. So I want you to label your line like this, and then put another set of little hatch marks in between each of those major ones, because in some cases we're going to use half-billion-year increments. As a reminder, this first half a billion years, or actually 542 million years to be more precise, is the Phanerozoic eon. And remember, we live right here. And the rest of this time is the Precambrian, and again, it goes a little bit farther back than I've shown. So what we're going to do is we're going to put on here information about oxygen in our atmosphere, oxygen being O2. And remember, the early atmosphere was mostly water vapor and carbon dioxide, not something that's very breathable. Remember that the earliest life that we know of, blue-green algae, was a photosynthetic organism, and the oldest fossil that we've been able to find is about 3.5 billion years old. So from this time onward, we have photosynthesis occurring. And so that's why I've drawn this line, and you should add that as well. So from that point on, carbon dioxide is being turned into oxygen. So let's make sure you're clear on photosynthesis. This is a process that plants undergo where they take in water, they take in carbon dioxide and light from the sun, and they produce sugar and oxygen. Now, what do we mean by sugar? Well, we mean the material of the plant. So this summer, I think a lot of us during COVID-19 had a garden for lack of anything else to do, and a lot of us grew zucchini. So let's use zucchini as an example. So the plant takes in water, light from the sun, carbon dioxide from the atmosphere, and you get the actual zucchini, which represents the sugar, and it gives off oxygen. Now, the reverse process of photosynthesis, the reciprocal process, is respiration, and that's what animals do. So we, as an animal, breathe in oxygen, we eat the zucchini, and we give off carbon dioxide and water. You might not realize, but you breathe out water vapor, and we also release heat. So these two processes are complementary and very important when it comes to life on Earth. So here we are back at our timeline, and now we're going to add some evidence from the rock record for the oxygen appearing in our atmosphere. The first piece of evidence we're going to add is something called a banded iron formation, and this is a type of rock that appeared about 3.5 billion years ago, maybe a little bit older, and is only seen in the rock record until about 2 billion years ago. I happen to have a banded iron formation right here, and I always pass this around the class. I'm sorry I can't do it. It is banded, if you can see it. It's got alternating layers of an iron-rich mineral called hematite, and then another mineral called jasper. And it is very heavy considering its size. It has a lot of iron in it, so it's very dense. So here's an outcrop showing a banded iron formation, and these are sometimes abbreviated BIFs. And as I mentioned, all of these BIFs were formed between about 3.2 and 2 billion years ago. So the idea is that oxygen levels increased in the oceans due to photosynthesis by the blue-green algae, and the oxygen combined with iron in the ocean, and it formed these rocks. Eventually, the iron in the oceans was used up, and so the oxygen that continued to be accumulating from the photosynthesis had nowhere to go but out of the oceans. And so oxygen began to accumulate in the atmosphere. And so that was a very important event. So the disappearance of BIFs from the rock record tell us when the oceans ran out of iron, but more importantly, when oxygen left the oceans and became abundant in the atmosphere. Another rock-related piece of evidence is something known as pyrite pebbles. So pyrite is sometimes known as fool's gold, and it's an iron-based mineral. And in the presence of oxygen, pyrite would rust, essentially. And so we don't see pyrite pebbles today in the presence of oxygen in our atmosphere. But in the past, from about 3.5 billion to about 2.5 billion years ago, we have evidence of pyrite pebbles that have been preserved in rocks. Here's an example of a rock that's been sliced with a diamond saw. You can see these little bits of gold-looking things. They're actually pyrite pebbles. So like I said, these would rust today, but in older rocks, they were preserved because there was no oxygen in the atmosphere yet to rust them. And so the disappearance of these, again, indicates oxygen accumulating in the atmosphere. Let's go to the next piece of evidence. This is a piece of evidence that tells us oxygen came into the atmosphere. And these are known as red beds. Red beds, like they sound, are red rocks. And I'm sure you've seen these if you've driven around the western US at all. These are sedimentary rock units, which we'll learn about later in the class, that have turned red because iron-bearing minerals have oxidized, which means rusted, in the presence of atmospheric oxygen. And this has only happened since oxygen's been available in the atmosphere. So red beds only came on the scene about 2 billion years ago. So now let's add the key to this puzzle, which is the Great Oxygenation Event. And you can just kind of shade this region here between about 2.5 to 2 billion years ago, or 2,500 million to 2,000 million years ago. This region is what we call the Great Oxygenation Event. This is when oxygen significantly increased in our atmosphere, and anaerobic bacteria, which I've mentioned a while ago when we talked about extinctions, were no longer able to thrive, and aerobic bacteria that do like oxygen and other organisms that like oxygen as well were able to take over. So again, this is when atmospheric oxygen levels greatly increased. Another thing that happened as oxygen built up in our atmosphere is the O2 that we breathe became O3, which is ozone. And that ozone rose and formed the ozone layer in our atmosphere, another crucial event for life to exist on our planet. Next up, a brand new unit, plate tectonics. Unless, of course, you're in my Geology 3 course, and then we're going to continue on with astronomy.